Most people don't teach geology because they don't feel confident in teaching it, because they feel like they don't understand it themselves. You have to understand a topic before you can teach it. And true, there's a lot of information in geology that one needs to know to really master it. But to understand it doesn't require a lot. A little bit of chemistry, a little bit of learning a few new words, and you can understand about rocks, you can understand about minerals and weathering, all the basic concepts of geology. What's to follow is activities that you can use in your classroom to help you explain these principles to your students. Let's take a look at the chemistry first. You've all seen those periodic tables with all the elements on them, I think 105 by now. Of that 105, 92 of those are found in nature, the rest are made by man. And of the 92, 88 of those are found in the earth itself. Now, if you held the earth up and weighed it and said, what is the most abundant element? The right answer would be iron. But in fact, if you look at just the crustal material alone, you'll find that only 8 elements make up most of the crust. In fact, 99% of the crust is comprised of only 8 of those 88 elements. And that's really all we're concerned about, because we're looking at the rocks on the surface of the earth. Well, what are these 8 elements? The most abundant one is oxygen. Practically half the weight of all the crustal material is tied up in oxygen, and it's not a gas, it's in compound form, it's tied up in compounds. The next most abundant element, another 30%, is silicon, that's Si on the chart. And then we have some metals, we have magnesium, we have iron, and we have aluminum. And then we have some calcium and sodium and potassium. Those are the 8 most abundant elements in the Earth's crust. It stands to reason that the most common materials found on the surface of the earth are materials that are made by combinations of these 8 elements. As the molten rock, the liquid rock, comes near the surface and cools, some of the material crystallizes out at different temperatures. This material we call minerals. Now, there's over 2,000 minerals that have been identified so far. Some are very rare, like the precious stones, diamonds and rubies and sapphires, and gold too is very rare. Those minerals are made of elements that are not in that group of 8. And the common minerals that we find all over the surface of the earth, like quartz and graphite and mica, these minerals are made from those 8 elements. Now, more specifically, what is a mineral and how does it differ from a rock? Well, to be a mineral, it has to fit 5 basic requirements. First, a mineral is an inorganic substance. This means that it never was alive. Second, a mineral is always a solid. Third, a mineral was formed in nature by natural processes. Things like pearls made by oysters or coral reefs are not considered minerals. Next, a mineral is formed in crystalline shapes, and there's about 7 or 8 different shapes that minerals may take. And lastly, and most importantly, is a mineral has a uniform chemical composition. This means that every piece of sapphire is made of the same chemical elements in the same combination. Now, how does a mineral differ from a rock? Well, a rock is a combination of 1 or more minerals. So the chemical composition of the rock would be different throughout. And a mineral is pure. Let us now take a look at some activities that reinforce these concepts. What we want to demonstrate in this activity is how minerals are formed. And although most minerals form when liquid rock turns to a solid, some minerals form when water evaporates and leaves the crystals behind. A perfect example is halite, or common ordinary salt. Salt is called an evaporite, and as the water evaporates away, it leaves little tiny cubes of salt behind. I haven't had too much success growing real large crystals of salt in this type of setup, but I have looked at some other chemicals that make really beautiful crystals. One of those is alum, and alum forms a 4-sided double pyramid. It's like a 4-sided pyramid and a 4-sided pyramid, and they're stuck together. Very beautiful crystalline shape, and it grows very rapidly. You want to do it as a demonstration though in your class, and do it early in the day so you can observe the little string hanging in the jar throughout the day. Now what I did is I used this whole 3-ounce bottle, or about 7 tablespoons of alum, in 1 cup of very hot water, almost boiling water. Because the water's hot, more alum goes into solution. The water is holding all the alum it can. Then you dangle the string with a small weight on it inside the liquid. As the liquid cools off, these little spaces between the water get smaller and smaller, and the alum can't stay in the liquid anymore. It has to go somewhere. And it finds that little nucleus hanging on the string, and it says, hey, I'll just go over there and jump on that. So it starts, and it starts building one crystal, and that one crystal gets bigger and bigger, and eventually, after it gets layers and layers upon itself, you can start to see it. This is an experiment that you can show your students one way that minerals are formed, and invariably they will go home and try it on their own. As we make further investigations with crystals, we realize that there's some important questions that must be answered. One of these we can deal as an experiment, and the question is, does a crystal grow larger when it's cooled slowly or when it's cooled rapidly? We can easily test this by using the same chemical we used before, alum. Here it is, 2 parts water and 1 part alum. The students will have 3 samples. One sample in the Dixie cup of this liquid will cool in hot water, almost boiling water. Another sample will cool down covered by sand, insulated. A third sample will be put in a jar of ice water. I've sealed all 3 tops with saran wrap and a rubber band so that the air doesn't influence them. The heat or the cold will stay in. The question is, will we have larger crystals in the one that cooled slowly in the hot water, the one that cooled even slower in the sand pack, or the one that cooled very quickly in the ice water? This is very important for 2 reasons. Number 1, it explains the size of the minerals. And number 2, it explains how igneous rocks are formed, why some igneous rocks have large crystalline minerals in them, and other igneous rocks have minerals that are so small we can only see with a microscope. They've cooled quickly. And the ones with the large crystals never quite made it to the surface, and they've cooled much slower. As we look further into the topic of minerals, we find some real interesting things. For example, there's over 2,000 known minerals, but only a small number of these make up most of the Earth's crust. These are called the rock-forming minerals. And the family of minerals that is the most common are the silicates. The silicates are the minerals that are formed by those 2 elements, silicon and oxygen. And one of the most common of silicates, found as an ingredient in granite, is quartz. Quartz's chemical formula is SiO2, 1 atom of silicon to 2 atoms of oxygen. Another common mineral found in granite, and also a silicate, is feldspar. Feldspar is a compound of silicon, oxygen, and several other elements. If we look closer at granite, we start to see some other minerals like hornblende and mica. Now there's lots of minerals in the world, and the task is sometimes upon us to identify a mineral, and it can be a difficult task. There's certain physical properties that we can look at, properties that we can test, and then we can look up in tables to find out what that particular mineral might be. These physical properties are what we're going to take a look at next. If you conduct an activity in mineral identification in your class, it's important that you start small first, because there's so many minerals out there, it's sometimes very confusing trying to identify one from another. There are some basic physical properties, though, that help us to identify these minerals. These properties are luster, hardness, streak, and density. And we're going to review them one at a time. First, we'll take luster. There's 2 basic groups of minerals. The metallic minerals, as you see here, and the non-metallic minerals, as you see over here. If the mineral gives off a metallic glisten to it, no matter what color it is, it's considered a metallic mineral. The non-metallic minerals are the duller ones and the transparent ones like quartz. Another property to investigate is streak. Streak is the color that a mineral makes when it's scratched across one of these dull porcelain squares. For example, this is hematite. It's supposed to streak red. And this is galena. It's supposed to streak gray. This is just one of some of the properties that you would use to help identify a mineral. As you go on, you would investigate the property of hardness. Hardness is a scale from 1 to 10, and it determines how hard a mineral is. If it's got a hardness rating of 1, it's very soft. If it has a hardness rating of 10, like a diamond, it's very hard. When we look at hardness, we look at what the mineral will scratch and what will scratch the mineral. Now, for example, a piece of talc here can be scratched by a fingernail. As we go up in the hardness scale, we get to fluorite, which is a 4 on the hardness scale, and quartz, which is a 7 on the hardness scale. And here I have a piece of corundum, which is 9 on the hardness scale. If you take something very hard like corundum or diamond and a piece of glass, you can test its hardness because it should scratch glass. This property, along with the other properties, help us to identify unknown minerals. The property of luster, streak, and hardness. If we need to look further into other properties to identify the mineral, we might look at density. Density is the amount of compactness of the particular mineral. Some materials are light, seemingly light. Other materials are seemingly heavy, especially the metals. An experiment that you definitely should do is a rock identification. Get your students, give them samples, and try and have them identify what type of rock, one of the 3 main types that their sample is. 3 types: igneous, metamorphic, and sedimentary. The igneous rocks are the rocks that come from fire, okay, ignition and ignite. They're the rocks that come from inside the earth, that molten liquid rock down there that we call magma. 2,000 degrees or so. It comes up to the surface of the earth. Now it might explode out into the air and it would cool very quickly. And when it cools quickly, you get the tiny little fine crystals. Very small. Sometimes you can't even see them with a magnifying glass. If it cools slowly, this magma, then it's like near the surface of the earth, just under the earth, like in an oven, and it slowly cools down. Then you get the larger crystals, like granite is a perfect example. Crystals that you can see. This is where many of our minerals come from, in this type of rock that's called intrusive igneous rock. And of course the one that gets thrown out is called extrusive. The second type of rock is the sedimentary rock. They're usually easy to identify because they're made from sediments that are compacted together. And many sedimentary rocks have fossils in them. Here's a perfect example. So if it has a fossil in it, it's probably a sedimentary rock, and there's other rocks that don't have fossils in them that you can identify as sedimentary rocks because they're made from compacted sediments. Okay, the third kind of rock is called the metamorphic rock. And just as the name implies, metamorphic means to change. Like a caterpillar changes to a butterfly, it metamorphosizes. So do these rocks. They used to be either igneous rocks or sedimentary rocks, and they were under extreme pressure and heat from the weight of the earth pushing down on these rocks, and it rearranges the physical characteristics, the physical shape, the looks, and possibly the chemical composition of the rocks. In other words, some of the minerals change into other minerals because of the heat and pressure. So this rock is called the changed rock, and these rocks are the oldest rocks. So when you're looking at metamorphic rocks, you're looking at some of the oldest rocks on the earth. Now let's take a look at some samples of each of the 3 types, so it'll be easy for you to identify the rocks from your samples. Let's take a look at some igneous rocks. Remember, igneous rocks have either large crystals if they cooled slowly, or much smaller crystals, some very fine, if they cool quickly. Igneous rocks are usually multicolored, however there are some exceptions. These 2 rocks on the end here are granite. Notice that the granite has irregular edges. That's another property of igneous rocks. They're usually very rough and irregular. And the crystals are not in any particular pattern in the rock. They're just spread randomly throughout. If you hit an igneous rock with a hammer, it'll shatter and break into irregular pieces. Looking over here, this next thing is a piece of obsidian. Obsidian is a rock that you should know, and it comes from magma, that stuff that comes out of the earth and then is called lava when it's on the surface. When that magma cools very, very rapidly, the crystals don't have time to form. So this does not have a crystalline structure. And obsidian was used by Indians to make spear points and arrowheads, and this appears to be a spear point. There's lots of other igneous rocks. There's rhyolites and basalts and scoria, and even over here a little piece of pumice, which has a lot of air in it, and it's not even as dense as water. In fact, it floats in water. One of my favorite rocks. Over here I have a couple of samples that I recently collected when I went on a trip to Mount St. Helens. So these rocks are igneous rocks, and they're only a few years old. Sedimentary rocks. I have some great samples, but before we get to the samples, let me show you a good demonstration and a good experiment you can do with your students. First, a demonstration. You've probably seen it before. Get a large glass bottle or a long glass tube like I have here. Put different samples of items in there, like I have some small pebbles and then some muddy, silty material. Put some water in it, put your hand over it, shake it around a couple times so everything's mixed really good, and then let it sit and settle. And you and your students will see that the heavier rocks, the denser rocks, settle first, and then the finer materials, and we have a band here of finer material, and then even finer material which looks like silts right up here in the very top. So you start to get an understanding. This is how materials settle out, and this is maybe a way that sedimentary rocks are formed, and in fact it is. Then you get to the experiment, and I think a group of 3 is the minimum amount for this one. Use a black card so your students can see the background in the bottle. Any tall glass jar will work good. They'll want to measure the height so they know how far it's falling. What we're doing in experiment form, recording data, everything just like we do, is we're dropping sand grains into this water and recording the rate that it takes for it to hit the bottom from when it starts to when it hits. So you have to have a timer, and you'll have to have a recorder and then an observer to see when it starts and when it stops. This is a good activity because it gets the students to understand that different materials fall through water at different rates. And then you want to go from there and say, okay, well, let's look at these rocks, sedimentary rocks, and try and see that this is how they were formed. So now let's take a look at the sedimentary rock samples. Sedimentary rocks fall in 2 main categories too, what we call the clastic rocks and the non-clastic rocks. The clastic rocks, like this one has fossils in it, but they're formed when material settles out slowly and compacts itself. The non-clastic rocks are a variety of their own, and they're caused when water evaporates and leaves minerals behind. This particular one is found in mineral springs, and it's called tufa. This one next to it is also a non-clastic rock, and it's a common mineral called halite or salt, and you can test it easily by tasting it. This one over here would be a clastic rock, and it's called shale, and shale is nothing more than mud that's been compressed, where all the water's been squeezed out of it, and it's been turned into a rock, and it's now impervious to water. Water cannot pass through it. Next to the shale, we have kaolin. Kaolin is formed when very tiny particles settle out very slowly in very quiet waters, and it's a very light rock. Then the very familiar rock sandstone, and you can see where the layers took place here in the sandstone, and you can break sandstone apart quite easily with your fingers. In fact, for an activity, you can have students scrape a couple pieces of sandstone together, and they can see right away that it's a very soft rock. Finally, my last specimen here is a conglomerate. Conglomerates are cementations of all kinds of particles and rocks, and they're quite hard. To name particular sedimentary rocks might require a reference book on rock identification, but it shouldn't be too much trouble to be able to decide that a rock is a sedimentary rock, especially if it's loose and it has fossil materials and it's got layering in it. Now let's take a look at the final group of rocks, the metamorphic rocks. As you might guess, metamorphic rocks are also subdivided into 2 main groups, the foliated and the non-foliated. Now what does this mean? Well, foliated metamorphic rocks have visible bands of minerals in them. And not to be confused with sedimentary rocks, metamorphic rocks are very hard. They've been under lots of pressure. Here's some more foliation shown here. The non-foliated metamorphic rocks, here's a perfect example, marble. Marble is a single mineral rock. That's why you don't see other minerals in it. In fact, it's limestone, which is a sedimentary rock that's been put under lots of pressure. If we take sandstone and put it under lots of pressure, we get this rock, quartzite. If we take basalt, which is an igneous rock, and put it under pressure and metamorphosize it, we end up with serpentine. Next to the serpentine, we have two foliated rocks. These are slates, and these are caused from shales being put under lots of pressure. Then we have a schist. There's lots of different kinds of schists, but they're foliated, and this particular one is a mica schist. Now let's back up just a little bit and remember that igneous rock that we looked at, the granite. It has the feldspar and the quartz and the hornblende and so on in it. What would this look like if it was put under lots of pressure and metamorphosized? Well, it would come to look like this. And it's a very common metamorphic rock. It's called gneiss. And if you look very closely at it, you can see the bands of minerals that are lined up. Now we want to reinforce the idea that the minerals line up in bands in metamorphic rocks, in the foliated rocks. We've got two good activities to show this. If you've ever wondered what to do with all those stubby little crayons that are just too small to write with, here's the solution. And it's going to demonstrate how metamorphic rocks form. You set all the little crayons down on a piece of wax paper. Then you cover them with a paper collar and another piece of wax paper. Then you put a coffee can over the top of these and pour boiling hot water into it. In about 20 minutes after the water cools, you have the example of a metamorphic rock. Heat and pressure have fused the crystals together. This is also a good art activity. Using a ball of modeling clay and a bunch of washers, we can demonstrate how metamorphic rocks form. You insert the washers in a random pattern. We now have an igneous rock with the crystals not aligned in any particular way. Then we want to subject our igneous rock to extreme pressure. So we put it on a piece of wax paper, cover it with another, and sandwich it between two books. You might want to have a student stand on top of this to get the pressure required. Once you feel like you've put enough pressure on the rock, go ahead and open it up and take a look at it. You should have a metamorphic rock. And if you look closely, you find that all the crystals are lined up in the same pattern. This is why we get the bands in the rock, and you can have your students tear this apart to see that the crystals are all lined up.